Hello everyone, I welcome you in this lecture and today we are going to talk about Huffman coding algorithm. Huffman coding is a very important and interesting algorithm for compression and also for encoding the data. So let's see. We know that when we work with the computer, then all the information, all the data that we are feeding into the computer is stored into binary, that is in the form of zeros and ones. And because we are living in the age of internet and we always interested to share our information, so we need to share this information, transmit it information through different mediums. So we are always concerned about the security of the data, and also we want to transmit data in such a way so that it can be transmitted enough in a very fast way. Now, to transfer your data securely and fastly, two things will be required. One thing, that the size of the data can be reduced, can be compressed so that it will take less time to reach to the destination. So the compression is the one requirement to do the fast transfer. Now when we say encoding, encoding is basically required when we are interested to store our data or transmit our data from one medium to another medium. So encoding means how we are going to represent our characters, means the data that is actually based of character, how we are going to encode these characters into a binary form. So we have two kind of encoding scheme. One is called fixed length encoding and other is called variable length encoding. As you can see here, fixed length encoding and variable length encoding. In the fixed length encoding, every character is assigned a equal number of bits or a same number of bits. So if I am writing a plus k or a b c, here we can see three characters are there, a plus and k, and a b and c. And in my encoding I have used fixed length encoding. That means every character is assigned a equal number of bits. If I am assigning 8 bits to represent a, that means to represent this I need 24 bits. Now for here also we need 24 bits because every character is represented by the same number of bits. Even if I write a b c, so if you write here a is occurring 3 times, then b is occurring 1 time and c is occurring 1 time, and if I am using a fixed length encoding, in that case I need 8 into 5, that is 40 bits will be required. The next is a variable length encoding. Now, as we have seen in the fixed length encoding, we are assigning us same number of bits to each character, but in the variable length, as the name suggests, we are assigning each character a different number of bits. So the smart approach is the characters which are occurring frequently or the characters which are occurring maximum time will be assigned a few number of bits, so that the overall uh, representation in terms of bits will be reduced, and the characters who are occurring rarely or few number of times in the given text or in the given data will be giving large number of bits. So we'll see that how the things will be done. We'll move to the next slide. Now let us first take some example to understand in a better way. So we have given one string like A, A, B, A, C, D, A, D. This is a string where we can see some characters are involved here, A, B, C, and D. And the frequency of the characters A, B, and C in this given string is A is occurring 1, 2, 3, 4 times, B is occurring 1 time, C is occurring 1 time, and D is occurring 2 times. Now here A is occurring maximum number of times, so you can say this is for A, B, C, and D. So A is having the highest frequency, and then we have D, and then we have B and C. So based on the approach that we have discussed, that in the variable length encoding scheme, we assign the fewer number of bits to the characters who is occurring maximum time or whose frequency is maximum. So let us say we have assigned randomly these bits, that A is represented by 0, B is represented by 0, 1, 1, C is represented by 1, 1, 1, and D is represented by 1, 1. Now this is what we have assigned. This means if I write AA, BAC, DAD, then this is what I can get, because if I write A, B, A, C, D, A, D, then A means 0, then A means 0, then B means 0, 1, 1, then A means 0. That means if I write this string, this can be represented by this sequence of bit streams. So here you can see this is A, B, A, C, A, C, D, A, D. So if we have used the fixed length encoding where each character is having 8 bits, so here we have 1, 2, 3, 4, 5, 6, 7, 8. In that case we have used 64 bits would have been used to represent this particular string. But here you can see we have only used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have reduced a larger extent, up to larger extent we have reduced the size. But does it work? Does it able to represent the string that we want to encode? Let us see. Okay, so the strategy that we have discussed just now will have a problem. Now what is the problem with the strategy? Here we have assigned these encoding. A is given 0, B is given 0, 1, 1, B, C is given 1, 1, 1, and D is 1, 1. Now if we want to decode it, decode this string back to its original significance or the original data format, then what you will get? So if we go with this kind of scheme, then after decoding you may get multiple different outputs. That means we are not able to uniquely represent our string with our encoding scheme. Now how? Now see here, with the same sequence of bits we are able to get these many different strings. How? This is A, right? So this is A, we can get this, and then we have A, then we have D, then A, then we have C, then we have this 1, 1 we have used for D, then A, and then D. So this is one representation. Similarly, instead of this, now here you can also assume that 0 we have taken separately, but now you can also take in pair. So 0, 1, 1 means B. So instead of taking AA, we would have taken this as B. Similarly, here also instead of taking this separate A, we would have chosen this in combination, and then it becomes AAB. So that means with the same sequence of bit stream we are able to get different strings, which is not correct. So this is a kind of problem. Every string must have a unique representation of bits, then only we can make any significance, then only it has a meaning. Now what is the solution for this? So the solution for this is we need to apply the prefix rules property. Now with the prefix rule property we can avoid such ambiguities. Now here you can see there are a lot of ambiguities are there. Ambiguities means there is no clarity. We have many combinations are possible. So we need to go with some mechanism, and one popular mechanism to avoid such scenario or to avoid such circumstances or avoid such problems is go with the prefix rule. Now prefix rule says that no binary code should be a prefix of another code. So we need to assign each character a bit combination in such a way that no character can have this combination as a prefix. What does it mean? It means if I am assigning A is equals to 0, that means if I assign 0, 1, 1 to B, then this is not following the prefix rule, because in this assignment this 0 is actually the prefix which is actually assigned to some other character. Now we need to avoid this kind of situation. So the prefix rule says that any assigned bit combination should not be acting as a prefix to any other character. Okay, so if we follow the prefix rule, then this kind of ambiguity can be avoided. So let us take one example. Okay, so let us take one example. Here we have apply the prefix rules, and we have assigned a equals to 0, means a can be represented by 0 in the bit format. Then b character will be 1 1, c will be 101, d will be 100. Now here you can see that there is no assignment will violate is actually violating the prefix rule. Now because 0 is given here, then there is no 0 occurring here, because 1 1 is given here, so you can see that there is no 1 1. If you see this 101, then there is no 101 is occurring. So if we use this format and we want to decode uh, the bit stream, then we will get back exactly the string that we have encoded. Now here you can see that this is what we have started with, and this is what we have encoded. And while decoding, what we will do, we will keep on reading the bits, and on getting a combination that we have assigned here, we will convert into the character. So we get 0, 0 means A, then 0, 0 means A, then 1, 1. So when you read 1, so actually we have to read 1, 1 character. So when you read 0, this is A, then you read 0, this is A, then you read 1. Now there is 1, there is with a single 1 there is no character assigned, so you have to read a next bit. Now 1, 1. So with 1, 1 you get this B. Then we have 0, that is A. Then we have 1. Now with 1 there is with single 1 there is nothing is given. Then 1 0. Then with 1 0 we don't have anything assigned. Then we have 101. So 101 means C. So here you can see that we can very easily decode this bit stream to our actual string, and there is no ambiguity generated. Now the question arises that how we can assign these kind of assignments, how can we make this kind of assignments which follows the prefix rule. Here actually we have only 4 characters, so manually we can do the assignments which will follow the prefix rule. But if you are working for a larger data set where we have large number of characters, then doing manually is actually not a easy process. It will be very complex. So we need to look some algorithm that can provide this kind of encoding scheme that will take care of prefix rule, and this is what the Huffmann coding provides us. So let us see what is Huffmann algorithm. So Huffmann encoding is the algorithm that we are interested to discuss here. It is developed by David Huffmann in 1951. This is a very interesting technique and very important technique used in the compression as well as for encoding. Now this technique is based on variable length encoding. That means for every characters we are not assigning equal number of bits, but depending on the frequency we are assigning the size of the bits for each character. So the scheme is depending on how frequently they occur in the given text. So this is the logic. Now we'll see the algorithm. We will see the step by step that what this algorithm says, and then we apply this algorithm to one case in order to understand that how the characters are assigned the bits. Create a leaf node for each character and build a mini heap using all the nodes. So for each character we need to we are going to make one tree, and this is said to be a Huffmann tree. So the tree is consisting of nodes. So here we need to construct a leaf node for every characters. For every individual character, we will make one leaf node. And in this algorithm, we are going to actually build a min heap. Min heap is a binary tree in such a way that the root node is having a minimum value or the less value than the child. The frequency value is used to compare the two nodes in the min heap. So here we are representing each character as a node, and this node is actually also having one frequency value. Frequency value represent that how many times this character is actually occurring in the given string. Step 2. Repeat step 3 to 5 while heap has more than one node. So we have to do something in a loop from 3 to 5 until we reach or until we left with one node. When you reach to the situation when only one node is left, that means you have processed the entire algorithms and we reach to our solution. Now what is required? Extract two nodes, say x and y, with minimum frequency from the heap. So already we have in the first step we have assigned each character as a node, and each node will be having the frequency of its occurrence. So from the given set of nodes we will pick two nodes with the minimum frequency and then construct our heap. Create a new internal node Z with x as its left child and y as its right child, and the frequency of Z is the frequency of x plus frequency of y. So the very first thing is we need to pick the two nodes with having which are having the least frequency, and then we will build a heap out of this. And when we construct a new node, this new node we will call it as let's say n1 or n2, and the frequency of this node is the addition of the frequency of x and y. So if x and y we are going to pick, then we are going to make a new node, let's say n1, and if the frequency of x is 5, y is 6, and then this n1 frequency will be 11. Add z to the min heap, and this is like basically becomes a part of our heap that we are actually constructing in this process. Last node in the heap is the root of the Huffman tree. So we need to keep on doing this process again and again until we are left with the single node. And when we are left with the single node, that node is actually the root of our Huffman tree. And with the help of that tree, we are able to generate our bit sequence that is assigned to each character. How? Let us take one example. Now, so we'll continue with the same example that we have discussed so far. We have A, B, A, C, D, A, D. This is what the string given to us. And here the frequency of A is 4. So let us uh, go as per the Huffman algorithm. So the very first thing is you need to represent every character as a node. So we have a node A, and the frequency of this is 4. So you can write it like this. Then we have B, the frequency of this is 1. Then we have C, the frequency of this is 1, and then we have D, the frequency of this is 2. So arrange the characters in the ascending order of their frequency and apply the Huffman algorithm. So let us arrange all this in the ascending order. So B is having the minimum frequency, and then we have C, then we have D, then we have A, because we need to construct our tree based on the minimum based on the node with the minimum frequency. So here first we will pick the nodes with the minimum frequency. So we will pick B and C. So this is B with frequency 1, and then we have a C with frequency 1, and then with this we will construct a heap. We will just make a new node, let's say N1, and with the frequency adding the 2, this is 2. So B becomes the left child, C becomes the right child. We have already included these two nodes in our tree which we are constructing. Then we will pick the next node, So here we have a node with the frequency 2, so we will going to add in our tree. So we will take this D with frequency 2 and we will going to construct it like this. So we will going to make one new node and 2 and frequency with 4. Then we keep on moving in this way. So what is next? We have 4 here and 4 here. Now one thing to keep in mind that this is 4, this is 4. So we are going to add it here. But let's say we have some character. This is just for example. We have something, let's say E with the frequency 3. And then we have something, let's say J with the frequency 3. In that case we would have not added this E and J directly here, but we would have picked this E and J separately here. So we would have said E3 and J3 and added to let's say N3 with 6, and then we keep on doing like this. Means every time you have to pick the node with the least frequency, with the minimum frequency available. So since this is not existing here, so we are not considering this, but I just took this case so that you can understand that what to do if there is the node existing which is less than the 4 or which is less than the frequency that we have achieved so far. So if you have some node with the lesser frequency, with the frequency which we have achieved so far, so you can just construct separately and later we can join it as we move further. So here you can see now we have, this is 4, this is 4, so that means we have to pick the 2. So we will take this A 4 and then we have to add this. So we'll get a new node, let's say N3, and this is 4 plus 4 is 8. So this is now all nodes are actually included and we are left with a single node. So we have to stop here, and actually we are able to get our uh, bits now for each character. So now see here, we will go like this: left side, right 0 and 1. So in the tree left, so with every structure, every no a tree and subtree, we just go like this. To the left child we assign, to the left branch you can say we assign 0 and then 1 and 0 and 1. So what we will get now, A is here, we have to start from here, from the root. So A is here. Now to reach to A, we have to traverse with one edge. This is 0. Now to traverse to then we have to traverse to D. So D you can traverse with 1 0, and then you have to traverse to B. B you can traverse with 1 1 0, and then C you can traverse with 1 1 1. So you can see here A is 0 and B is 1 1 0, C is 1 1 1 and D is 1 0. Now if you look at this, you can find that A is the most frequently occurring character, and this is only assigned 1 bit, and B and C is the least occurring character, so we have assigned 3 bits. Now the result of this kind of strategy is the overall size of the bit stream will be reduced. So here you can see here this is 8, that means that you can encode the entire this by using 8 bits. So with 8 bits only we can able to reduce, so we are able to compress it. So this is a very fantastic compressing algorithm. We can compress our data by using this strategy. So we have seen that how it helps us to encode the data, and also it will compress our data. So this is a very interesting and important algorithm for compressing and encoding. This is all for this lecture. Thank you very much.